Imagine you're standing at the edge of a cliff looking down at a deep canyon. On one side, you have a pile of raw, messy data, and on the other, you have clear, meaningful classifications, neatly separated into different groups. How do you get from one side to the other? That's where Fisher's linear discriminant comes in. Today, we're going to explore a powerful statistical technique that helps us draw clean, meaningful boundaries in complex data. Whether you're dealing with medical diagnostics, financial risk assessments, or even facial recognition, understanding how to separate different classes efficiently is crucial. But here's the thing. Many classification techniques struggle when classes start overlapping or when the data is just too high-dimensional. If you've ever worked with machine learning models that seem to get lost in a sea of features, you know exactly what I mean. Fisher's linear discriminant is designed to cut through that noise, finding the most effective way to separate groups while reducing the complexity of the data itself. So, what exactly makes Fisher's approach so effective? Why has it stood the test of time since 1936 and still remains a cornerstone of modern classification techniques? Well, that's exactly what we're about to find out. Let's get started. Imagine you're working on a classification problem. Maybe it's distinguishing between cancerous and non-cancerous cells, sorting spam emails from real ones, or even identifying fraudulent transactions in a sea of financial data. The challenge, the data isn't neatly separated, some features overlap, some are irrelevant, and the sheer number of variables makes it difficult to visualize a clear boundary. How do you make sense of it all? This is exactly where Fisher's linear discriminant, FLD, comes in. It's a powerful statistical technique that allows us to project complex data onto a lower dimensional space while preserving the most discriminative information. It's not just about classification, it's about simplifying the problem while maximizing the separation between different categories. And trust me, when you're dealing with real-world data, this kind of efficiency is a game changer. Developed by Ronald A. Fisher in 1936, this method remains one of the most widely used tools in machine learning, pattern recognition, and statistics. Why? Because it works. Unlike traditional classification techniques that might struggle with high-dimensional data or overlapping classes, FLD takes a mathematical approach to find the optimal boundary, one that ensures classes are as far apart as possible while keeping intra-class variance to a minimum. Think of it like this. Imagine you're a detective trying to separate suspects based on their alibis, fingerprints, and whereabouts. Some evidence overlaps, some are noise. But your job is to find the most telling clues that clearly distinguish one suspect from another. Fisher's method does something similar. It picks the most relevant features, reducing complexity while keeping the classification sharp. But what makes FLD different from other classification methods? How does it compare to linear discriminant analysis, LDA? And what are its practical applications in finance, healthcare, and artificial intelligence? These are exactly the questions we're about to answer as we dive into the theory, applications, and future directions of Fisher's linear discriminant. Get ready, because this is going to be both insightful and practical, and by the end you'll see exactly why this method remains a cornerstone in modern classification problems. To truly understand Fisher's linear discriminant, we need to take a step back and explore its origins. The story begins in 1936 when the British statistician Ronald A. Fisher introduced a groundbreaking concept that would go on to become a fundamental pillar in statistical classification and machine learning. At the time, the challenge was simple but crucial. How do we separate different categories of data in a way that is both efficient and mathematically sound? Fisher's solution was elegant. He proposed a method that would find the best possible linear boundary between two or more groups while ensuring that the separation was maximized. This was the birth of linear discriminant analysis, LDA, a technique that would evolve into what we now call Fisher's linear discriminant, FLD. But let's go deeper. Why was this method so revolutionary? Before Fisher's work, classification problems were often solved using trial and error methods or overly simplistic decision rules. Fisher introduced a systematic mathematical approach, leveraging the idea that class separation could be maximized by analyzing variance, specifically by maximizing the ratio of between-class variance to within-class variance. This concept remains at the heart of modern classification techniques today. After Fisher's initial work, LDA quickly gained traction. By the 1940s and 1960s, researchers started formalizing its mathematical framework and adapting it for broader applications, everything from biology and social sciences to early machine learning models. As computational power grew in the 1970s and beyond, LDA became a staple in pattern recognition, image processing, and AI-driven classification tasks. However, as more complex datasets emerged, researchers started recognizing limitations in LDA, particularly when dealing with overlapping classes, high-dimensional data, and real-world noise. This is where Fisher's linear discriminant, FLD, took center stage, refining LDA by introducing a more sophisticated approach to feature selection and dimensionality reduction. So, why does this matter today? Because FLD remains one of the most effective and computationally efficient methods for classification, even in the era of deep learning. Its influence can be seen in everything from facial recognition to medical diagnostics and financial risk assessment. Now that we understand where Fisher's method came from, let's explore its limitations and the challenges that it addresses in modern classification problems. Linear discriminant analysis, while powerful, has its share of limitations that can make it challenging to apply in real-world scenarios. One of the most common issues is that it works best when the number of features is smaller than the number of observations. This becomes a major hurdle in cases where datasets have a high number of dimensions, such as image recognition, genomic analysis, or financial risk modeling, where the number of features can easily outnumber the sample size. In such situations, the method loses its effectiveness, leading to overfitting and poor generalization to new data. Another major challenge with LDA is dealing with overlapping classes. The method assumes that different categories of data are well separated, but in reality, many data sets don't behave that way. Consider medical diagnoses, where symptoms of different diseases may overlap significantly, or fraud detection, where legitimate and fraudulent transactions can share similar characteristics. In these cases, the method struggles to establish a clear boundary, increasing the likelihood of misclassification. LDA is also highly sensitive to outliers. Because it relies on calculating means and variances for each class, a few extreme values can heavily distort the decision boundary. This is particularly problematic in finance, where a handful of highly unusual transactions could skew an entire fraud detection model. Without proper handling of outliers, the model can make inaccurate predictions and fail to generalize effectively. Another fundamental assumption of LDA is that the data follows a normal distribution. However, in reality, many datasets do not fit this assumption. Financial data often exhibits long tails. Customer behavior data can be highly skewed, and biological datasets frequently contain multimodal distributions. When the assumption of normality is violated, the performance of LDA deteriorates, making it less suitable for certain classification problems. Despite these challenges, the ideas behind LDA laid the groundwork for improvements that address its weaknesses. This is where Fisher's linear discriminant comes into play. It refines the approach by introducing better optimization techniques and a more flexible way to select features, making it far more robust for handling complex classification tasks. Moving forward, understanding the mathematical foundation of Fisher's approach will show why it remains such an important tool in modern machine learning and statistical analysis. Fisher's linear discriminant builds on the foundation of linear discriminant analysis, but takes it a step further by optimizing the way class separation is achieved. The goal is to find a projection that maximizes the distance between different classes while minimizing the spread within each class. This results in a classification model that is not only more effective in distinguishing categories, but also reduces the overall complexity of the dataset by projecting it onto a lower dimensional space. This makes it particularly useful for high-dimensional problems where traditional methods struggle. At the core of Fisher's method is the idea of maximizing the ratio of between-class variance to within-class variance. To understand this, imagine plotting two categories of points on a graph. The key challenge is to find the best possible line that separates them. Instead of simply drawing a boundary, Fisher's method finds the optimal direction in which the data can be projected to achieve the maximum possible separation between the categories. By doing this, it ensures that the overlapping between classes is minimized, leading to a more robust classification. This approach is especially powerful in real-world applications where clear-cut boundaries do not naturally exist. In fields like medical diagnostics, Fisher's linear discriminant can be used to analyze patient symptoms and test results to determine the likelihood of a disease, even when some overlap exists between healthy and affected individuals. In financial modeling, it can help distinguish between low-risk and high-risk borrowers by focusing on the most relevant factors that contribute to creditworthiness. Unlike other classification techniques that may require extensive feature engineering or complex transformations, Fisher's method works by defining two key scatter matrices: the within-class scatter matrix, which measures how spread out the data is within each class, and the between-class scatter matrix, which quantifies how far apart the classes are from each other. By solving an optimization problem that balances these two quantities, the method identifies a direction that provides the most meaningful distinction between groups. The real advantage of Fisher's linear discriminant is that it doesn't just classify, it also simplifies the data. Instead of working in a high-dimensional space where classification can be computationally expensive and prone to overfitting, it projects the data onto a lower dimensional subspace while preserving the essential characteristics needed for separation. This is particularly useful in machine learning, where reducing dimensionality can lead to faster training times, improved generalization, and more interpretable models. This ability to both classify and reduce complexity makes Fisher's linear discriminant a widely used technique in pattern recognition, image processing, and artificial intelligence. Next, we will explore the exact mathematical steps that make this technique work and see how it compares to traditional linear discriminant analysis in practical applications. Fisher's linear discriminant is built on a strong mathematical foundation that allows it to efficiently separate different classes of data. At its core, the method relies on maximizing the ratio of between-class variance to within-class variance, ensuring that different categories are as distinct as possible while minimizing the spread within each class. This is achieved through a series of carefully designed calculations that define the optimal projection direction for classification. The first step in this process is understanding class variance. The within-class scatter matrix is calculated by measuring how much data points within each class deviate from their respective class means. This provides a sense of how compact or spread out each category is. At the same time, the between-class scatter matrix is computed, which represents how far apart the class means are from each other. The goal is to find a projection that maximizes the separation between class means while minimizing the dispersion within each class. Once these scatter matrices are defined, the next step is to determine the optimal projection direction. This involves solving a generalized eigenvalue problem where the eigenvalues and eigenvectors of the matrix formed by the inverse of the within-class scatter matrix multiplied by the between-class scatter matrix are computed. The eigenvector corresponding to the largest eigenvalue provides the most effective projection direction as it maximizes the separation between categories. This projection is crucial because it allows the data to be mapped onto a lower dimensional space where classification becomes easier and more robust. Instead of dealing with multiple variables and complex relationships, Fisher's linear discriminant reduces the problem to a single direction that captures the most meaningful differences between classes. This not only improves classification accuracy, but also enhances computational efficiency, making it ideal for high-dimensional problems. One of the reasons Fisher's method remains so effective is its ability to handle scenarios where traditional classification methods struggle. By focusing on the discriminant ratio rather than arbitrary decision boundaries, it can deal with overlapping classes more effectively, making it highly useful in medical diagnostics, financial risk assessment, and facial recognition. This optimization-based approach to classification is what sets Fisher's linear discriminant apart from other methods. Unlike naive classification techniques that simply try to separate data using predefined rules, this method finds the best possible separation mathematically, ensuring that the classification is both accurate and stable across different data sets. Now that we have established the mathematical foundation behind Fisher's method, the next step is to compare it with traditional linear discriminant analysis to understand how it improves upon existing classification techniques and why it remains one of the most widely used approaches in modern machine learning. Fisher's linear discriminant and linear discriminant analysis share a common goal: to classify data by finding the best possible separation between categories. However, Fisher's method introduces key refinements that make it more robust, particularly when dealing with high-dimensional data and overlapping classes. Understanding these differences is crucial to appreciating why Fisher's approach remains widely used in classification tasks today. Linear discriminant analysis was originally designed to find a linear combination of features that best separates different classes. It works by assuming that the different categories follow a normal distribution and that the covariance matrices of all classes are equal. This assumption simplifies the problem, but introduces limitations when real-world data deviates from these conditions, when class distributions have different shapes, or when the number of features exceeds the number of observations. LDA struggles to produce accurate classifications. Fisher's linear discriminant improves upon LDA by focusing on maximizing the ratio of between-class variance to within-class variance. Instead of assuming identical covariance matrices across all classes, Fisher's method directly optimizes the projection that best distinguishes the groups. This approach makes it more effective in situations where class distributions overlap or where traditional statistical assumptions do not hold. Another key advantage of Fisher's method is its ability to reduce dimensionality while preserving discriminative information. In many machine learning applications, datasets contain a large number of features, many of which are redundant or irrelevant for classification. By projecting data onto a lower dimensional space that maximizes class separability, Fisher's method not only improves classification accuracy, but also enhances computational efficiency. This makes it particularly useful in applications such as image recognition, fraud detection, and medical diagnostics, where large feature sets need to be analyzed quickly and accurately. One of the biggest limitations of LDA is that it assumes well-separated classes with distinct decision boundaries. However, in many real-world scenarios, class distributions are not perfectly separated, and simple linear boundaries may not be sufficient. Fisher's method addresses this by ensuring that the projection chosen provides the maximum possible separation, even when there is some overlap between categories. This ability to handle complex classification problems makes it a preferred choice in high-stakes applications where accuracy is critical. By refining LDA's approach and making it more adaptable to real-world data, Fisher's linear discriminant has become a foundational tool in classification tasks. As machine learning and artificial intelligence continue to evolve, techniques like this remain essential for developing models that can make sense of high-dimensional, overlapping, and complex datasets. With a clear understanding of how Fisher's method compares to traditional LDA, the next step is to explore its real-world applications and see how it is used in practice across different industries. Fisher's linear discriminant is more than just a theoretical concept. It has real-world applications across multiple industries where classification and dimensionality reduction play a crucial role in decision-making. From healthcare to finance and even artificial intelligence, this method helps solve complex problems by identifying the most meaningful features that separate different classes. One of the most well-known applications of Fisher's linear discriminant is in facial recognition systems. In image processing, faces are represented as high-dimensional data with thousands of pixels contributing to each image. Using Fisher's method, facial features are projected onto a lower dimensional space, retaining only the most relevant characteristics needed for classification. This significantly improves recognition accuracy while reducing computational complexity, making it an essential technique in security systems, smartphone authentication, and biometric verification. In the healthcare industry, Fisher's linear discriminant plays a key role in disease diagnosis. Medical data often contains overlapping features, making it difficult to distinguish between different conditions. For example, in cancer detection, patient samples may have slight variations that make classification challenging. By applying Fisher's method, doctors can project patient data onto a lower dimensional space that highlights the most distinguishing features, improving early detection and reducing misdiagnosis rates. In genomic research, it is also used to classify gene expression patterns, helping researchers identify potential disease markers. Finance is another area where Fisher's method is widely applied, particularly in credit scoring and fraud detection. Financial institutions rely on classification techniques to assess the risk of loan applicants and detect fraudulent transactions. Traditional methods struggle when different financial behaviors overlap, making it difficult to identify risky borrowers or fraudulent activities. Fisher's linear discriminant helps by finding the optimal projection that separates high-risk from low-risk individuals, leading to better decision-making in credit approval and fraud prevention. In computer vision and object classification, Fisher's method is used to improve the accuracy of automated systems. In self-driving cars, for example, real-time object detection is critical for identifying pedestrians, road signs, and other vehicles. By applying Fisher's method, the system can efficiently differentiate between objects based on their key characteristics, improving safety and reducing false detections. Beyond these fields, Fisher's linear discriminant is used in speech recognition, customer segmentation, and various machine learning applications where classification and feature reduction are necessary. Its ability to enhance separation between classes while maintaining computational efficiency makes it a valuable tool in any scenario where data needs to be classified accurately with minimal loss of information. Understanding its applications helps illustrate why Fisher's method remains a fundamental technique in data science and artificial intelligence. Now, let's take a closer look at how to implement Fisher's linear discriminant step by step, breaking down the process into a practical workflow that can be applied to real-world datasets. Implementing Fisher's linear discriminant involves a structured process that transforms raw data into a meaningful classification model. The goal is to project the data onto a lower dimensional space while maximizing the separation between different classes. This step-by-step approach ensures that the classification is both accurate and computationally efficient. The first step is data pre-processing. Before applying Fisher's method, it's essential to clean and normalize the dataset. This means handling missing values, removing outliers, and scaling features so that they have a mean of 0 and a standard deviation of 1. Normalization ensures that features with different scales don't dominate the projection process, leading to more stable results. Next, the mean vectors for each class are computed. This involves finding the average value of each feature for every category in the dataset. These mean vectors represent the central tendency of each class and are crucial for understanding how the classes differ from one another. Additionally, the overall mean of the dataset is calculated, which helps measure the separation between classes. Once the means are determined, the within-class and between-class scatter matrices are constructed. The within-class scatter matrix measures how much the data points deviate from their respective class means, capturing the spread within each group. The between-class scatter matrix quantifies how far apart the different class means are from each other. These matrices are the foundation of Fisher's method, as they define the variance structure that needs to be optimized. The next step is solving the generalized eigenvalue problem. By computing the eigenvalues and eigenvectors of the matrix formed by the inverse of the within-class scatter matrix multiplied by the between-class scatter matrix, the optimal projection direction is determined. The eigenvector corresponding to the largest eigenvalue represents the best direction for projecting the data while maintaining class separability. Once the optimal projection is found, the data is transformed into the new feature space. This means that each observation in the dataset is projected onto the computed linear discriminant axis. Instead of working with multiple features, the dataset is now represented in a lower dimensional space where classification is easier and more robust. The final step is model evaluation. After projection, classification can be performed using a simple threshold or a nearest neighbor approach. The model's performance is then assessed using metrics such as accuracy, precision, recall, and F1 score. A well-implemented Fisher's linear discriminant should show strong separation between classes while maintaining computational efficiency. This step-by-step workflow highlights why Fisher's method is so powerful. By systematically reducing dimensionality while preserving key class information, it provides a practical solution for classification problems in machine learning, pattern recognition, and artificial intelligence. With an understanding of how Fisher's method is implemented, the next step is to see it in action. Let's explore a real-world case study in healthcare where Fisher's linear discriminant is used to improve disease diagnosis and medical decision-making. Fisher's linear discriminant has been successfully applied in healthcare, particularly in disease diagnosis and medical decision-making. One of the most compelling examples is its use in predicting diseases such as diabetes and cardiovascular conditions, where early detection can significantly improve patient outcomes. By analyzing patient data, including symptoms, lab results, and risk factors, Fisher's method can help distinguish between healthy individuals and those at risk of developing a condition, enabling doctors to make faster and more informed decisions. In a study involving a dataset of 1,000 patients, Fisher's linear discriminant was applied to classify individuals into two groups, those with diabetes and those without. The model was trained using key health indicators such as blood glucose levels, body mass index, and cholesterol levels. By projecting this high-dimensional data onto a lower dimensional space, the method was able to enhance classification accuracy while reducing noise from irrelevant features. The results were impressive, with the model achieving an accuracy rate of 92% in distinguishing between the two groups. This level of performance is critical in healthcare, where misclassification can lead to delayed treatment or incorrect diagnoses. Beyond diabetes detection, Fisher's linear discriminant has been widely used in cancer research. In oncology, early detection of malignant tumors is essential for increasing survival rates. By analyzing biopsy results and medical imaging data, Fisher's method helps separate malignant and benign cases with greater precision than traditional statistical approaches. One of the key advantages is its ability to handle overlapping features, which is often the case in cancer diagnostics, where some benign and malignant cases may share similar characteristics. The ability to maximize between-class variance while minimizing within-class variance ensures that the classification is as accurate as possible. Another major advantage of Fisher's method in healthcare is its ability to reduce misdiagnosis rates. In many cases, diseases exhibit overlapping symptoms, making it difficult for even experienced medical professionals to distinguish between conditions. By applying Fisher's approach, hospitals and medical researchers can develop models that provide clear decision boundaries, assisting doctors in diagnosing conditions more confidently. Studies have shown that using Fisher's linear discriminant can reduce misclassification rates by up to 15%, leading to better patient outcomes and more effective treatments. Beyond diagnostics, Fisher's method is also used in genomic data analysis, where it helps differentiate between various genetic expressions. This has been particularly useful in identifying biomarkers for diseases, allowing researchers to pinpoint genetic variations that contribute to different health conditions. By reducing the complexity of genetic data while retaining essential classification information, Fisher's approach has played a significant role in advancing personalized medicine. With its ability to enhance classification accuracy while handling complex medical data, Fisher's linear discriminant continues to be a valuable tool in healthcare. The next case study will explore its impact in finance, where it is used to assess credit risk and detect fraudulent transactions, two areas where precise classification is equally critical. Fisher's linear discriminant is widely used in finance, where accurate classification is essential for risk assessment, fraud detection, and credit scoring. Financial institutions rely on machine learning models to determine whether a loan applicant is a low-risk or high-risk borrower, and Fisher's method provides a mathematically sound approach to making these decisions. By analyzing historical financial data and identifying key patterns, it helps banks and credit agencies reduce default rates while improving the efficiency of lending decisions. One of the most significant applications of Fisher's linear discriminant in finance is credit scoring. Traditional methods, such as logistic regression, struggle when financial behaviors overlap, making it difficult to distinguish between borrowers who are likely to repay their loans and those who are at risk of defaulting. Fisher's method improves classification accuracy by projecting borrower characteristics, such as income level, credit history, debt-to-income ratio, and past payment behavior, onto a lower dimensional space where the separation between high-risk and low-risk individuals is maximized. A case study conducted at a major financial institution demonstrated the power of Fisher's approach in risk assessment. By applying Fisher's linear discriminant to a dataset of loan applicants, the model was able to improve default prediction accuracy by 15% compared to traditional logistic regression models. The results showed that the method provided a clearer distinction between creditworthy applicants and those likely to default, leading to better informed lending decisions. Another major financial application is fraud detection. In the banking industry, fraudulent transactions often share similar patterns with legitimate transactions, making it difficult to identify fraudulent activities using simple rule-based systems. Fisher's method is particularly effective in fraud detection because it helps financial institutions identify subtle differences in transaction behavior that indicate potential fraud. By analyzing transaction features such as amount, frequency, location, and spending habits, the method creates a projection where fraudulent activities stand out more clearly against normal transactions. Financial institutions have successfully used Fisher's linear discriminant to detect fraud in credit card transactions, online banking activities, and wire transfers. In one study, applying Fisher's method to a dataset of transactions helped reduce false positives by 20%, ensuring that legitimate transactions were not incorrectly flagged while still catching fraudulent ones with high accuracy. This balance is crucial for improving customer experience while maintaining security. Beyond fraud detection and credit scoring, Fisher's method is also used in stock market analysis and investment risk assessment. By classifying stocks based on historical price movements, volatility, and financial indicators, it helps investors identify assets that align with their risk tolerance and investment strategy. The ability to separate stable stocks from volatile ones is particularly useful in portfolio management, where diversification and risk control are key to long-term success. The financial industry is heavily dependent on data-driven decision-making, and Fisher's linear discriminant provides a powerful way to extract meaningful patterns from complex datasets. Its ability to improve risk assessment, reduce fraud, and enhance investment strategies makes it an essential tool in modern finance. Now that we've explored its applications in both healthcare and finance, let's take a look at the key advantages of Fisher's linear discriminant and why it remains a preferred classification method across various fields. Fisher's linear discriminant is widely regarded as one of the most effective classification techniques, offering several key advantages that make it a preferred choice in fields ranging from finance to healthcare, computer vision, and artificial intelligence. Its ability to both classify and reduce dimensionality makes it highly efficient, particularly in scenarios where datasets contain large numbers of features that need to be simplified while preserving essential information for decision-making. One of its most important advantages is improved classification accuracy. Fisher's method maximizes the ratio of between-class variance to within-class variance, ensuring that different categories are as distinct as possible. This means that even in cases where class distributions overlap, the method still finds the best projection for separating them. Empirical studies have shown that Fisher's method can improve classification accuracy by up to 20% compared to traditional methods, making it a powerful tool for applications where precise classification is critical. Another major benefit is dimensionality reduction. Many real-world datasets contain hundreds or even thousands of features, making classification models computationally expensive and prone to overfitting. Fisher's linear discriminant simplifies this problem by projecting the data onto a lower dimensional space while retaining the most relevant information. This leads to faster training times, reduced computational costs, and models that are easier to interpret. In high-dimensional applications such as image recognition and genomic data analysis, this reduction in complexity significantly enhances performance. Fisher's method is also highly robust to overlapping class distributions. Traditional classification techniques such as logistic regression and simple decision boundaries often struggle when classes are not clearly separated. By focusing on maximizing class separability through an optimized projection, Fisher's method ensures that classification remains effective even in complex datasets. This is particularly beneficial in areas like fraud detection and medical diagnostics, where different categories often share similar features and need to be carefully distinguished. Another advantage is its ability to handle imbalanced data sets more effectively than some other classification techniques. In real-world scenarios, some classes may have significantly more data points than others, which can cause models to favor the majority class. Fisher's method ensures that even smaller classes are adequately separated, leading to better balanced predictions in applications like risk assessment, cancer detection, and financial modeling. Additionally, Fisher's linear discriminant is computationally efficient, especially when compared to more complex classification algorithms. While deep learning models require large amounts of data and significant computing resources, Fisher's method provides a mathematically optimized solution with relatively low computational cost. This makes it an excellent choice for applications where real-time decision-making is required, such as real-time facial recognition and high-frequency trading. The ability to both classify and simplify data while maintaining high accuracy makes Fisher's method one of the most widely used classification techniques. However, like any method, it is not without its challenges. Next, we will explore some of the key challenges in implementing Fisher's linear discriminant and how they can be addressed in practical applications. While Fisher's linear discriminant offers numerous advantages, it also comes with certain challenges that must be addressed when applying it to real-world problems. Like any statistical method, its performance is influenced by the structure of the data, the assumptions it relies on, and the computational complexity involved in high-dimensional applications. Understanding these challenges is essential for making informed decisions about when and how to use this technique effectively. One of the primary challenges is dimensionality reduction limitations. While reducing the number of features can improve efficiency, there is always a risk that important information may be lost in the process. If the projection discards key features that contribute to class separation, the classification accuracy may suffer. Careful feature selection and pre-processing are necessary to ensure that the most relevant information is retained. Another issue is sensitivity to outliers. Since Fisher's method relies on mean and variance calculations, extreme values can have a significant impact on the scatter matrices used for classification. If an outlier shifts the mean of a class, it can distort the projection direction and reduce accuracy. This makes robust pre-processing techniques essential, such as outlier detection and removal before applying Fisher's method to a dataset. Fisher's method also assumes that the data follows a normal Gaussian distribution, which is often not the case in real-world datasets. Many datasets exhibit skewed distributions, multimodal patterns, or heavy-tailed behavior. When the normality assumption is violated, the method may not produce optimal results, and alternative classification techniques like support vector machines, SVM, or neural networks may perform better. Another challenge is data requirements. Fisher's linear discriminant requires a sufficient number of samples per class to estimate class means and variances accurately. If a dataset is imbalanced or has too few observations in one class, the method may struggle to establish a reliable projection. This is especially problematic in fields like medical research or fraud detection, where some conditions or fraudulent behaviors occur less frequently, leading to class imbalances. Data augmentation techniques or resampling strategies can help address this issue. Computational complexity is another factor to consider, particularly when dealing with high-dimensional data. The method involves calculating the inverse of the within-class scatter matrix, which can be computationally expensive if the dataset has many features. In such cases, dimensionality reduction techniques like principal component analysis, PCA, can be used before applying Fisher's method to improve efficiency. Despite these challenges, Fisher's linear discriminant remains a powerful and widely used classification technique. By understanding its limitations and applying the right pre-processing strategies, it can still be one of the most effective tools for feature selection and classification in machine learning. As research continues to evolve, new methods are emerging to enhance Fisher's approach and integrate it with more advanced machine learning techniques. The next section explores some of the future directions for Fisher's linear discriminant, including how it is being adapted for modern artificial intelligence and big data applications. As machine learning and artificial intelligence continue to evolve, Fisher's linear discriminant is being enhanced and integrated into more advanced methodologies, while the core principle of maximizing class separability remains unchanged. Researchers are finding new ways to improve its efficiency, scalability, and adaptability for modern applications. The future of Fisher's linear discriminant lies in its ability to merge with other techniques and adapt to the growing demands of big data, deep learning, and real-time analytics. One of the most promising developments is the integration of Fisher's method with deep learning frameworks. Traditional deep learning models, such as neural networks, require large amounts of data and often struggle with interpretability. By incorporating Fisher's linear discriminant as a feature selection or dimensionality reduction step, researchers can improve classification accuracy while reducing computational complexity. This is particularly useful in areas like image recognition and speech processing, where reducing dimensionality before feeding data into deep networks can lead to faster training times and better generalization. Another important direction is the use of Fisher's method in hybrid models. Instead of relying on Fisher's approach alone, modern classification systems are incorporating it alongside support vector machines, SVMs, random forests, and ensemble learning methods. By combining Fisher's ability to optimize class separation with the flexibility of machine learning algorithms, these hybrid models can achieve higher accuracy, better handling of non-Gaussian data, and improved robustness to outliers. Advancements in computational efficiency are also expanding the usability of Fisher's linear discriminant. Traditionally, one of the challenges of Fisher's method has been the need to compute the inverse of the within-class scatter matrix, which becomes computationally expensive for large data sets. Researchers are now developing parallel computing techniques and GPU acceleration to significantly reduce processing time, making it feasible to apply Fisher's method to massive datasets in fields like financial analytics, real-time fraud detection, and high-frequency trading. Another exciting development is the application of Fisher's linear discriminant in bioinformatics and genomics. With the rapid growth of genetic research, classifying gene expression patterns and identifying biomarkers for diseases has become a major focus. Fisher's method is proving to be an effective tool for analyzing high-dimensional biological data, helping researchers uncover genetic variations linked to diseases and paving the way for more personalized medicine and targeted treatments. In computer vision, Fisher's linear discriminant is evolving to handle more complex and dynamic image classification tasks. Traditionally used in facial recognition, it is now being adapted for object tracking, gesture recognition, and autonomous driving systems. By integrating it with convolutional neural networks, CNNs, and reinforcement learning, researchers are enhancing its ability to handle real-world, unstructured visual data more effectively. As artificial intelligence systems continue to advance, Fisher's linear discriminant will remain a valuable tool for classification and feature selection. Its ability to optimize class separation, reduce dimensionality, and integrate seamlessly with modern machine learning techniques ensures that it will continue to play a key role in pattern recognition, data science, and AI-driven decision-making. Now that we've explored its evolution and future potential, let's summarize the key takeaways and the lasting impact of Fisher's linear discriminant across various fields. Fisher's linear discriminant has proven to be a powerful and enduring method for classification and dimensionality reduction, influencing a wide range of fields from machine learning and finance to healthcare and artificial intelligence. By maximizing the ratio of between-class variance to within-class variance, it provides an optimized projection that enhances classification accuracy while simplifying high-dimensional data. One of its most significant contributions is its role as a foundation for advanced techniques. Many modern classification algorithms, including neural networks and ensemble learning methods, build upon the principles introduced by Fisher's approach. The concept of finding the most discriminative features is a key element in feature selection and representation learning, making Fisher's method a critical stepping stone in the development of more sophisticated AI models. Across industries, Fisher's linear discriminant has demonstrated versatility in handling complex classification problems. In healthcare, it has improved disease diagnosis and genomic research by distinguishing between subtle variations in medical data. In finance, it has helped assess credit risk and detect fraud by optimizing decision boundaries in transactional data. In computer vision, it has played a central role in facial recognition and object classification, enhancing security systems and automation. Beyond its real-world applications, Fisher's method is valued for its computational efficiency and interpretability. Unlike black box models such as deep learning, Fisher's approach provides a mathematically sound explanation for why certain features contribute to classification. This makes it a preferred choice in industries where explainability is critical, such as medical research, legal decision-making, and regulatory compliance. At the same time, its limitations have driven new innovations. Challenges related to outliers, high-dimensional data, and assumptions about normality have led researchers to develop hybrid models, deep learning integrations, and alternative discriminant analysis techniques. As AI and big data continue to evolve, Fisher's method will likely be refined further to adapt to real-time analytics, streaming data, and large-scale classification problems. The lasting impact of Fisher's linear discriminant is evident in its widespread adoption and continued relevance in modern data science. While new machine learning techniques continue to emerge, the fundamental principles of Fisher's method, maximizing class separability, reducing complexity, and improving classification efficiency, remain as important today as they were when first introduced in 1936. Understanding Fisher's linear discriminant not only provides insight into traditional classification techniques, but also lays the groundwork for leveraging more advanced methodologies. Whether applied to artificial intelligence, financial modeling, medical diagnostics, or computer vision, this method continues to shape the way data is classified, analyzed, and used to drive meaningful decision-making in the modern world.